Welcome back to part 2 of Introduction to Abstract Mathematics, and we're still talking about the functions. Just a quick reminder of our table of content. Today in this video we will talk about the injective function. So all our focus will be on the injective function. The next one will be about the surjective and bijective functions. So let's hop on section 4.2, injective functions. So what is injective functions? We have first to define what do we mean by a function to be injective. So I will start with a function f from a to b is said to be injective. Sometimes the same word as injective, we say 1 to 1, or sometimes in short we just write 1 1. F for any x1 x2 in the input a, we have f of x1 is equal to f of x2. So if we have 2 points, they have the same output, they have the same image, then those 2 points actually are the same. It must be the same, and this is the definition for the injectivity. So here what we have if we have f of x1 equal to f of x2, then x1 must equal to x2. So this is what we mean by injective functions. Now if we look at an arrow diagram, let me just zoom in here. In the arrow diagram, if this is A and this is P, for example, if this is 1, 2, and 3, and here A, B, and C, this means each one must correspond to only one element, something like this. So each one of these has only one arrow related to it, or let's say maximum one arrow. Maybe there is no arrow at all, that's fine, but there must be one arrow. We cannot have this and this go to the same output. This is not injective. So injective means in the arrow diagram that any output is only related to one. So this is what we call it 1 to 1. One input goes to one output. Now, it could happen that some of the output has nothing. For example, this one, and this one. This is fine. This is still injective. Why? Because each output is only related to one input. So it is 1 to 1. Now, some of them are left over. This is okay. This is a different story, but that's fine. But at least each one of these is only related at maximum 1. So this is what we call it 1 to 1 function. Now, we have a quick notation here. We write A, and then we write this arrow to mean that there exists an injective function. F from A to B. In that case, we also say, sometimes you will see this one in many books, and we will use it later on. Sometimes we say A is embedded in B. So A is embedded in B, it means there is an injective from A to B, and sometimes we use this arrow, especially put attention to this part. It means that there is injective from A to B. There is injective that A can be seen as part of B. It means there is an injective function. So this is the definition of injective function. again, if we want to show that a function is injective, remember this statement is something of the form B implies Q. And in order to prove B implies Q, we can use direct proof and we can use contrapositive as well as contradiction. So this is kind of if B, then Q. So let's see the strategy before we start, and from there we go on. To show a function is injective, as I said, we can use the direct proof approach as well as the contrapositive and contradiction. I didn't write the contradiction here because usually direct proof will solve 90 or maybe 90%, 80 to 90% of the problems, while contrapositive will only solve some of the problem, and maybe contradiction will not be used so frequent in this context to prove a function is injective. Now what's the direct proof? As usual, we assume B, we do many steps, and hopefully we reach Q. So B to Q. The contrapositive approach, we assume the conclusion is not satisfied, and we prove that the assumption is not satisfied. So not Q, do many steps to get not B. Now, on the other hand, if we want to show that the function is not injective, what we need to do is we need to find x1, x2, specific value for x1, x2, such that the assumption hold, but the conclusion not. So this is what we need to find. We need to find two different values for x1 and not equal to x2, such that the images are the same, they are mapped, their images is the same, the output is the same, but they are actually not the same. So which means x1 is not equal to x2. This is if we want to show that the function is not injective. And we shall see it now in the next couple of exercises. We will practice how we prove that a function is injective. So I will go to example 1. And example 1 is telling me that I need to show that a function from the integers to the integers, taking x as an input and give me 3x minus 2 as an output, I need to show this function is injective. So if we write it in the usual function notation, this means f of x is just 3x minus 2. Now, I would advise you to pause this video and to assume f of x1 is equal to f of x2 and try to do many steps and see if you can reach that x1 is actually equal to x2. So please the video and then you can watch it. Otherwise, we can just solve it with each other here. So to prove, we will use the direct proof approach. So assume f of x1 equal f of x2. Now what is f of x1? This is just 3x1 minus 2 equal, what is f of x2? We just replace x by x2, 3x2 minus 2. Now I can see there is a cancellation, negative 2 with negative 2. So I will get 3x1 equal to 3x2. Another cancellation, the 3 and the 3. So finally, I think I reach where I want to reach is x1 equal to x2. So all what I did is algebraic manipulation and I get x1, x2. So hence f is injective or 1 to 1. So we finished the first example here. All what we need to do is using the direct proof. We have to show that f of x1 equal to f of x2. Do the algebraic manipulation, cancel here and there, and get where we want to get. Let me move to example number 2. In example number 2, I need to show that a function is actually not injective. Well, as I said, to show a function is not injective, we need to find x1, x2. They are not the same, but when we apply f to them, we get the same results. Well, sometimes it's not clear how to find x1 and x2. So it is always good exercise is to try to see if you want to show this is injective, what will go wrong. So I will just have an analysis side to this, to here. So first of all, remember that f of x is just equal to x squared. I will go here and I will try to have a small box to see where things will go. Just analysis box. Something extra, you don't need it. Now, if you want to prove this is injective, I would assume f of x1 equal f of x2, which means x1 squared equal to x2 squared. Now, if I want to get rid of the square, I need to use the square root for both sides. So I just put square roots for both sides. And what you will get is the absolute value of x1 equal to absolute value of x2. Now, can we from here conclude that x1 equal to x2? The answer is no. There's a problem. Why? Because we cannot get rid of the absolute value. The absolute value sometimes is positive, sometimes is negative. So I cannot just take the absolute value and write it as x1. I need to know if x1 is positive, I will write x1. If x2 is positive, is x2. So this is correct if x1 is positive, x2 is positive, or both of them negative. Now, what happened if one of them positive, one of them negative? Of course, you cannot say they are equal. Now, when do we have two values, they have the same absolute value? And I think that the easy example is to use x1 equal to 1 and x2 equal to negative 1. Now, if we check, f of x1 will be just 1 squared, which is 1. If we check the other one, f of x2 is just negative 1 squared, which is equal again 1. Hence, the function is not injective. So again, to find a function is not injective is always a tricky business because we need to find x1 and x2, concrete values, specific values. Sometimes an analysis part will help me to see where my proof could go wrong if I try to prove it as injective. But this is of course not all the time, so we have to think and see where my proof will not go wrong. Let's move on to example number 3, which is this one. Example number 3. It looks like the same question as before, but the only changes is here in the domain. So changing the domain can change the function from not injective to injective. So injectivity must relate it to the function as well as the domain. You have to keep in mind. So here we need to prove that this function is injective. Let's see if we will get the same problem as before. So assume f of x1 equal f of x2, which means x1 squared equal to x2 squared. I'm taking the square root for both sides. And that would leave me with absolute value of x1 equal absolute value of x2. Now, because x1 and x2 are positive, or at least not negative, the absolute value will be the same. Remember, x1 and x2, they live here. They are positive, maybe 0, but that means the absolute value will be the same. So x1 equal to x2, and thus the function is injective. proof, this one, and that will lead me to write a note, so we don't forget. Injectivity depends on the function as well as the domain. Sometimes changing the domain will change the function from injective to not injective, or not injective to injective. And this is example number 3. Please pause the video, try to figure it out before we move to the last example in the injective section, which is example number 4. Example number 4 is a good way of exercising function from a set to set of sets, which is the power set. So here I'm taking my input is an element, and my output again is an element in the form of a set. We will get used to this, but at least for this context, let's just move the same way as we did. So we will use the direct proof approach. So assume f of x1 equal f of x2. Of course, x1 is this one, x2 is this one. Now, here I have two sets. Each set is singleton. This set has x1, this set has x2, and they are equal. That means there's only one way this could happen, which is that x1 is in fact the same as x2. Thus, my function is injective. Thank you for watching this video. Please watch the next video for the surjective definition as well as bijective definition.